In this lecture, we are going to discuss the Black-Scholes option theory. A plan. There are four parts of this talk. First, we will go over briefly the history of option pricing models. Then we will discuss the life and work of Fisher-Black, the main developer of the derivative theory. Third, we are going to derive Black-Scholes formula. This part is optional. It involves stochastic calculus. It is quite difficult. And last, we are going to calculate some examples with Black-Scholes models. The history of option pricing models. In 1900, Louis Bachelier developed the first mathematical model of Brownian motion and applied to option pricing. In the 1950s, Bachelier's work was rediscovered by Jimmy Savage and was translated by him into English from French. In the 1960s, Samuels and others developed option pricing formulas that contained expected return of stocks. In 1967, Thorpe and Kassoff published Beat the Market. This book contains many investment examples related to warrants, type long-term options. This further stimulated research interest in options. In 1973, Black and Scholes published the Black-Scholes formula. Merton also published a related paper. Louis Bachelier. Bachelier was a PhD student of Henry Poincaré, the most prominent mathematician of his time. In 1900, Bachelier published his PhD dissertation titled "The Theory of Speculation". He was the first to develop the mathematical model of Brownian motion and its application to option pricing. In his dissertation, he assumed stock prices follow random processes. Bachelier was a pioneer in stochastic calculus. His work was not much appreciated until several decades later. This is a picture of Louis Bachelier when he was about 20 years old. The discovery of Bachelier's work and the new progresses. Bachelier's work was discovered by Jimmy Savage, a mathematician and statistician, in 1950s. Subsequently, Samuelson and others developed option pricing theories. Their works contain expected return of the stocks, which are subjective. This makes their formulas less applicable in practice. Thorpe and Kassoff beat the market. In 1967, Thorpe and Kassoff published a book, Beat the Market. In the book, it discussed investment strategies involving warrants, such as long stocks and short overpriced warrants. At that time, both Thorpe and Kassoff were professors at the UC Irvine. Thorpe was a math professor and Kassoff was an economics professor. At that time, they developed a successful trading strategy, but they have difficulty find more funding. They published books to attract attention of potential investors. It stimulated further research in derivative securities. Thorpe is often considered as the father of quantitative investment. Thorpe and J. Reagan, a broker who read mid-market, found an investment partnership called Princeton Newport Partners. One strategy, the investment, was to short overpriced warrants and long underlying stocks. It was the earliest market-neutral investment practice. Since their trading positions are hedged against market movements, this type of investment funds were called hedged funds. Later, they are simply called hedge funds. However, trading positions in hedge funds are not necessarily hedged in today's hedge funds. This is the picture of Ed Thorpe. The influence of bid market. The book Bid Market is not about academic research. It is about the practice of investment. In a quote by Jack Trainer, he talked about the importance of practical experience. He said, practical experience is not merely the ultimate test of ideas. It is also the ultimate source. At their beginning, most ideas are dimly perceived. Ideas are most clearly viewed when presented as abstractions. Hence the common assumption that academics who are proficient at presenting and discussing abstractions are the source of most ideas. Black and Scholes. Black and Scholes developed option pricing formulas that we use today. They don't contain expected returns of stocks as a variable. Merton further developed the derivative theory. Broad applications of option theory. The derivative theory has found broader and broader applications in many areas. Importantly, it can be applied to many economic problems. The branch is called real option theory, as opposed to financial option theory. The life and the work of Fisher Black. Many people have attempted to work on option theory. Why Black and Scholes succeeded in the end. Jack Trainer developed Capam theory. From Capam theory, risk and return is the same thing, or they can be related by an equality. Fisher Black learned Capam from Trainer. He understood return can be dropped from the formula. Black-Scholes equation was first derived from Capam. It did not contain the term of the stocks. Fisher Black. Fisher Black started undergraduate program in physics. In physics program, He found Julian Schringer, his teacher in quantum mechanics, was extremely arrogant, so he switched to computer science from physics for his master's program. In the master program, he followed Marvin Minsky on artificial intelligence. Artificial intelligence is very hot today, but at Black's time, he found it lack substance. So in PhD program, he switched to mathematics and got his PhD in mathematics. After his PhD program, Black was looking for something practical. He joined ADR, a consulting firm. There he met Jack Trainer and learned finance economics from him. He applied what he learned from Trainer and developed Black Scholes theory. Later he moved to academia, first in Chicago and then to MIT. For the last 11 years of his life, he returned to industry at Goldman Sachs, starting from 1984. This is the picture of Fisher-Black. A few words about Fisher-Black's background from Jack Trainer, his mentor in economics and finance. Fisher never took a course in either economics or finance, so he never learned the way you were supposed to do things. But that lack of training proved to be an advantage, since the traditional methods in those fields were better at producing academic careers than new knowledge. Fisher's intellectual formation was instead in physics and mathematics, and his success in finance came from applying the methods of astrophysics. Lacking the ability to run controlled experiments on stars, the astronomers relies on careful observation and their imagination to find the simplicity underlying apparent complexity. In Fisher's hands, the same habits of research turned out to be effective for producing new knowledge in finance. The simplicity of Black-Scholes theory. Both Capam and Black-Scholes are thus much simpler than the world they seek to illuminate. But according to Fisher, that's a good thing, not a bad thing. In a world where nothing is constant, complex models are inherently fragile and are prone to breakdown when you lean on them too hard. Simple models are potentially more robust and easier to adapt as the world changes. Fisher embraced simple models as his anchor in the flux because he thought they were more likely to survive Darwinian selection as the system changes. Another quote from Jack Trainer, who wrote this after the death of Fisher-Black. Fisher's research was about developing clever models, insightful, elegant models that change the way we look at the world. They have more in common with the models of physics, Newton's laws of motion, or Maxwell's equations than with the econometric models. Lists of loosely plausible explanatory variables that now dominate the finance journals. John Cox said it best: Fisher is the only real genius I've ever met in finance. Other people, like Robert Merton or Stephen Ross, are just very smart and quick, but think like me. Fisher came from someplace else entirely. So where does Fisher Black come from? Why Fisher Black is the only genius? Can we achieve the same level of understanding as Fisher Black? Our learning objectives. First, we learn Black-Scholes theory. Then we apply Black-Scholes theory to understand equities, bonds, and other securities. Third, we will develop an economic theory of life and social systems from basic physical and economic principles. We show that the knowledge that helps Black succeed will also help everyone else succeed. There is really no mystery for Black's achievement. 3. The derivation of Black-Scholes formulas. The derivation of Black-Scholes formulas requires stochastic calculus. It is an advanced topic in mathematics. This part is not required. It is kept here because it is a great scientific achievement. We are going to have a look at the effects of variables on option pricing. The option we are considering is European call and put option and American call and put option. Small c is European call option, small p is European put option. Capital C is European or American call option, and capital P is American put option. Variable S is stock price, K is strike price, T time to maturity, sigma volatility, R risk-free interest rate, and D dividend. When the stock price increase, we know the call price increase, right? Because the call is to buy the stock price higher, so the value of the call is higher. On the other hand, put, its value is lower because put is to sell the stock, right? At a certain price. If stock price higher, then there's less chance to sell the stock at the price. And strike price K, when K is higher, the call price is lower because you need to pay K dollar to buy the stock. If the amount of payment is higher, then the value of the call is, and for the same reason, the value of put is higher. Time to maturity for the American call, American put, it's increase, right? Because the more time to exercise. To European call and European put, I mean, we would think longer T will be a higher value, but it's not exactly. We have to see, okay? For sigma, because option is an insurance, the higher the volatility, the more valuable the option becomes. For the discount rate, for call, it is positive because the higher discount rate, this means for the same amount of money you have to pay a strike price, the present value discounted back today is lower. That's why the call price will be higher, and similarly the put price will be lower. For dividend, a higher dividend, this means the less valuable the stock will be. So for call, it's lower price. For put, it's higher price. The concept under Black-Scholes method. Option price and stock price depend on the same underlying source of uncertainty. And essentially, the option price depends on the movement of stock price. So we can form a portfolio consisting of the stock and option, which eliminates this source of uncertainty because it's common uncertainty. The portfolio is instantaneously riskless and must instantaneously earn the risk-free rate. This leads to the Black-Scholes differential equation. Thorpe and Kassoff wrote a book, Beat the Market, in 1967. In that book, there is an investment example of long stock and short warrant. This provided the stimulus for this line of thinking. The derivation of the Black-Scholes differential equation. Assume stock price S follows the log normal process. ds is equal to mu s times dt plus sigma s times dc. So here dt is the time, right? And dz is the standard normal distribution. It's a random process. Suppose f is any derivative s or any function s. And derivative is really just a function, right? From Ito's lemma, is a basic result in stochastic calculus. df is equal to partial f partial s mu s plus partial f partial t plus 1/2 partial square f partial s square sigma square s square times dt plus partial f partial s delta sigma s times dz. So you can see, so what's the difference between Ito's lemma and this differentiation? In differentiation, there will be no second order term. There's no 1/2 partial square f over partial s square sigma square s square. It is there because of this randomness. The randomness add one more term. Okay, so we are not going to go over the detail here. If you want, you can check this Ito lemma. We set up a portfolio consisting of one short derivative and the long some number of shares. The number is partial f over partial s. Okay, whatever that number is. The value of the portfolio is given by negative f because we short the derivative plus partial s over partial f over partial s times s. S is the shares, right? We long this number of shares. The change in its value in time dt is given by negative ds plus partial f over partial s times ds. The portfolio form cancel this dz, yeah, because dz is the term of this randomness. But there is no more randomness, so the return must be risk-free rate. So this means the difference of portfolio is equal to R times the value of portfolio times dt. We substitute for df and ds in these equations to get the Black-Scholes differential equation, and that's the following equation. And what you can see is that the mu is the expected rate of return on stock disappear, right? Yeah. The equation looks quite complex, right? It's a second order partial differential equation. But any security whose price is dependent on stock price satisfies the differential equation. It is a very, very general equation because you see, the only assumption we give is that f is a function of s. So this means any derivative. We did not specify anything that gets the equation. So this is a very general equation. The particular security being valued is determined by the boundary condition of the differential equation. So we have a differential equation, we have the boundary condition we can determine. Or let me see, this is the initial condition or end condition, right? Yeah. So in the forward contract, the boundary condition is f is equal to s minus k when t is equal to t, time of maturity. So at time of maturity, we know the value of the contract. And the solution to the equation we can find out. Okay, yeah, it's a forward contract. The payoff structure of the call option. So we know when the call option contract matures. We know the payoff. The payoff is, suppose if the final price of stock is bigger than strike price, then the payoff is S minus K. If the final price is lower than the strike price, then the payoff is zero. So the value of call option time of maturity is equal to the maximum of S minus K or zero. So this forms the initial condition for the Black-Scholes equation. Solving the equation with the initial condition, we find the Black-Scholes formula for European call options. With a different initial condition, the put price initial condition is maximum K minus S or zero. We can find the Black-Scholes formula for European put options. Here are the Black-Scholes formulas. The European call option C is equal to S times ND1 minus K times E negative RT ND2. For European put, P is equal to K times E negative RT times N negative D2 minus S times N negative D1. Here, D1 and D2 are certain formulas. So it looks complex, so we try to go over them in more details. First, we discuss N. N is the cumulative distribution function. So at negative infinity, its value is 0. At positive infinity, its value is 1. So it's a probability distribution function. One may ask how to find a solution. The equation had been obtained quite a while ago by Fisher-Black, but they could not find a solution for some time. Later, they used formulas from others, which contain expected rate of return. They set the return to be the risk-free rate. That was the formula. It can be solved directly from the equation and the initial condition. The basic property of Black-Scholes formula, ignoring the cumulative distribution function, the Black-Scholes formula of call option becomes C equal to S minus K times E negative RT. Essentially, call option price is stock price minus the present value of the payment, strike price. So here K is the strike price, but it's discounted by the time, so E negative RT. And S is the stock price. Because the call option, we get the stock with the payment of K, right? But we pay K in the future, so the future value should be discounted. In the formula, D1 and D2 are not that intuitive, so we rearrange D1 and D2 into more symmetric way. So you can see that D1 is really log S over K E negative RT. So this means it's a ratio of the stock price over the strike price. But for D1, it's a little bit above the middle one. It's like 1/2 of the standard deviation. Because sigma square root t is the standard deviation. So D1 is really the middle plus 1/2 standard deviation. D2 is the middle one minus half of the standard deviation. So here, then it becomes more clear. Properties of Black-Scholes formula. When S over K times E negative RT increases, the chances of exercising the call option increases. From the formula, D1 and D2 increase, and ND1 and ND2 become closer to 1. That means the uncertainty of not exercising decreases. The difference between D1 minus D2 is 1 standard deviation. When sigma increases, D1 minus D2 increases, which suggests ND1 and ND2 diverge. This increases the value of the call option. There are similar properties for put options. We can look at negative D2 and negative D1. So their difference is also 1 standard deviation. Now we work on some examples. Example 1, calculating option prices. The stock price is 42. The strike price for European call and put option on the stock is 40. Both options expire in 6 months. The risk-free interest is 6% per annum and the volatility is 25% per annum. What are the call and put prices? Solution. We list the variables S equal to 42, K equal to 40, R equal to 6%, sigma equal to 25%, T equal to 0.5. 6 months is half year. Then we can calculate D1 and D2. The call price will follow the Black-Scholes formula. So C is equal to S ND1 minus K E negative RT ND2. We get 4.71. Similarly, P is equal to 1.53. Okay, now let's do an Excel calculation. First, let's input the parameters. The share price is 42 and the strike price is 40 for both call and put. And the risk-free rate is 6%. And the time to maturity is half year. It's 6 months. And the volatility is 25%. So we calculate D1 and D2. Let's input D1. D1 is equal to log B1 over B2. Stock price over strike price plus the R plus sigma square over 2, right? Times T before, yeah, the time to maturity before, and divided by sigma square root T. Sigma is B5 and the square root T is 0.B4. Okay, so we get B1, and D2 is equal to D1 minus R it's a sigma times square root of T, right? So is D1 is B6 and sigma is B5 times square root time T is B4. Okay, so that's D2. With D1 and D2 ready, we can calculate a call price and the put price. First, let's do a call. Okay, the call is the share price SB1 times ND1. So this normal distribution is a Excel function is norm. This means normal distribution because the standard distribution S is T and D1 is B6, right? And this function can return two values, either cumulative distribution or probability density distribution. When we say true, it returns cumulative distribution. That's what we want. And so it's SND1 minus KB2 times exponential negative RT, right? R is B3, T is B4, okay? Times ND2. ND2, again, N is norm as this. D2 is B7, and we say it's true, okay? So now let's return. We get the call price is 4.71. And now let's do the put price. The put price is K times exponential negative RT, right? So it's K times exponential negative RT times this negative D2. So negative B7 is a cumulative distribution minus B1. B1 is the S times n negative d1, negative v6, and true. So now let's return. We get this d2. The volatility. The volatility of an asset is the standard deviation of the continuously compounded rate of return in 1 year. As an approximation, it is standard deviation of the percentage change in asset price in 1 year. We can estimate volatility from historical data. In practice, we often use implied volatility. Implied volatility of an option is the volatility for which the Black-Scholes price equals the market price. There is a one-to-one correspondence between prices and implied volatilities. Traders and brokers often quote implied volatilities rather than dollar prices of the options. Causes of volatility. Volatility is usually much greater when the market opens than when it is closed. For this reason, time is usually measured in trading days, not calendar days, when options are valued. Dividends. European options on dividend-paying stocks are valued by substituting the stock price less the present value of dividends into Black-Scholes formulas. Only dividends with ex-dividend dates during life of option should be included. The dividend should be the expected reduction in the stock price expected. Example 2. Calculating option price with dividends. Consider European call option on a stock when there are ex-dividend dates in 2 months and 5 months. The dividend on each ex-dividend date is expected to be $0.50. The current share price is $30. The exercise price is $30. The stock price volatility is 25% per annum, and the risk-free interest rate is 7%. Time to maturity is 6 months. What is the value of the call option? Solution. The present value of dividend is $0.50 discounted by 2 months. That's 2 over 12 times 7%. And plus $0.50 discounted by 5 months. That is 5 over 12 times 7%. The result is 0.9798. So it's slightly less than $1 because it's $2.50 discounted. So the new as the stock price, the equivalent stock price is 30 minus 0.9798 is equal to 29 something. The rest is the same. K is equal to 30, R equal to 7%, sigma equal to 25%, and T 6 months is equal to 0.5. We can calculate D1, D2, and get the call price $2.0682. Investment strategies and outcomes. With options, we can develop many different investment strategies that could generate high rate of return in different scenarios. If will turn out to be right. However, we could lose a lot when market movement differed from our expectation. Option is a high leveraged investment. Example 3 is about investment in option. Suppose there are 4 investors, each with $10,000 initial wealth. One investor is a traditional investor. He used $10,000 to buy stocks. One is bullish about the market and buy call option on the stock. One is bearish about the stock and buy put option on the stock. One believes the market will be stable and sells call and put option to the second and third investors. Here are some relevant parameters. The stock price is $20. The strike price for both call and put is 20. Risk-free interest rate is 3%. Time to maturity is 6 months or half a year for both call and put. Volatility sigma is 30%. With these parameters, we can calculate D1, D2, and then call and put price. Here, the call price is 1.83 and the put price is 1.53. The number of call options the second investor buy is 10,000 divided by the call option price we get is more than 5,000 call options. The number of put options the third investor buy is 10,000 divided by put option, which is over 6,000 put options. Final wealth of 4 investors with different levels of final stock price. The final stock price can be $20, which remain the same as the initial stock price, or drop to $15 or rise to $30. So when for the first investor, if stock price remain at 20, his wealth will remain at 10,000, just as the initial wealth. If the stock price drop to 15, his wealth will be 7,500. If the share price rise to 30, his final wealth is 15,000. So you see, stock is a linear investment. If stock price drop by 50% or 25%, then its wealth will lose 25%. If the stock price will rise by 50%, his wealth will rise by 50%. For the second investor, if the stock price is 20 or 15, he will lose everything. And when stock price 30, his final wealth is over $54,000. It's 5 times the initial wealth. So you see, the option investment is a non-linear investment. So even the final stock price remain the same, he could lose everything. But once the market moves to his direction, he can make a lot of money. For the third investor, he buys put option. So when the market drops a lot, he makes a lot of money. Market dropped to $15. His final wealth is over 32,000. But when market is at 20 or 30, his final wealth is zero. For the fourth investor, he sells both call and put options. If the market stays at 20, does not move, he keeps all his premium he got from second investor and third investor, which is 20,000, plus his initial wealth, so he had 30,000. But if market moves either up or down, he not only loses all his money, but he's in deficit. He could lose a lot. That's why selling options are very dangerous. Usually, the sellers of options are the institutions with a lot of capital. Here is another example about investment with options. Example 4. 4 investors are bullish about stock. Each has $10,000 to invest. Current stock price is $100 per share. The first investor is a traditional one. She invests all her money to buy shares. The second investor buys call option with strike price at 100. The third investor buys call option with strike price at 111. Both options will mature in 6 months. The fourth investor buys call option with strike price at 110. The option will mature in 3 months. The risk-free interest rate is 3% per annum, compounded continuously. The implied volatility of options is 20% per annum. For simplicity, we assume the dividend yield of the stock is 0. If the stock price ends up at 100, 110, and 120 respectively after 3 months or after 6 months, what is the final wealth of each investor? What conclusion can you draw from the results? Here's the solution. The stock price is 100. Strike price is 100 or 110. Time to maturity can be half a year or a quarter year. Volatility sigma 20%, risk-free interest rate 3%, and from these parameters we can calculate D1, D2, and call option in 3 different kind of scenarios. The total investment is 10,000. So we can calculate the number of options bought in each cases. Suppose the final stock price at 3 months is 100, 110, 120. So the last investor, the investor who bought options that mature in 3 months, his final wealth would be 0, 0 over 90,000. Over 90,000. So you see, he either loses everything or he makes out money. And suppose the final stock at 6 months is 100, 111, 120. The first investor, his final wealth would be 10,000, 11,000, or 12,000. It's a linear investment. It's a stock. The second investor, if the stocks stop at 100, he loses everything. At 110, 120, his earning is quite substantial. His strike price at 100. And third investor, his strike price is at 110. So when the stock price is at 100 or 110, he loses everything. At 120, his final wealth is 38,000. Put call parity is a very important result in option theory. Let's consider the following two portfolios. Portfolio A, the European call on stock plus the present value of the strike price in cash. Portfolio B, European put on stock plus the stock. Both portfolios are worth maximum of the stock price and the strike price at the maturity of the options. So they must therefore be worth the same today. This means that C, the call, plus K times E negative RT, that's the cash in of present value of the strike price, is equal to put plus stock. An alternative way to derive put-call parity from the Black-Scholes formulas, we have call minus put is equal to SND1 minus K E negative RT ND2. That's the call price minus put price. We rearrange these terms to find they are equal to S minus K E negative RT. So this is the put-call parity. In example 5, we will consider arbitrage opportunities from the put-call parity. Suppose that the call price is $3, the stock price $31, time to maturity is 3 months, risk-free rate is 10%, strike price is 30, there's no dividend. So what are the arbitrage possibilities when P is equal to 2.25 or $1? Solution. The put-call parity is C plus K E negative RT is equal to P plus S. From this put-call parity, the put price is equal to C plus K E negative RT minus S. And we plug in all the relevant numbers, we find the put price should be $1.26. If the market price of put option is 2.25, it is overpriced. When something is overpriced, we should sell it or short it. So we can short put option together with stock, because remember in put call is T plus S. Right? So when we short put option, we short the stock as well, and we long at the same time we long the call option. So arbitrage profit is the market price minus the theoretical price. Market price 2.25, theoretical price 1.26. So we get 0.99, almost $1 profit. If the market price of put option is $1, it is underpriced. So we can long put option together with stocks. So we long put and long stock. Same time we short call option. Arbitrage profit is 1.26 minus 1 equal to $0.26. Example 6 is another example about arbitrage. A 6-month European call option on a non-dividend paying stock is currently selling at $5. The stock price is 64. The strike price is 60. The risk-free interest rate is 8% per annum for all maturities. What opportunities are there for an arbitrator? Solution. So we list all the parameters. Stock price 64, strike price 60, time maturity 6 months, risk-free rate 8%. Call option price $5. So from put call parity, we can calculate C plus K times E negative RT. It turned out to be 62.6. We know from put call parity, it should be equal to P plus S. However, S alone is $64. So this means the call is underpriced or the stock is overpriced. So we long call and short stock. Excel file. All Excel calculations can be found at the following file.